Thank you, Stanley. So good afternoon, everyone. So first of all, I would like to thank Professor Parimal and all the CNI organizers for providing this opportunity. So like said, today I'll be presenting our work that's controlled spatial sharing of GPU for scalable and efficient ML inference at edge. So this is a joint work done in collaboration with my advisor, Professor K.K. Ramakrishnan, and student Aditya Dakal from University of California, Riverside. The brief outline of my talk today is as here. So as we go along, I will try to cover these aspects in broader detail. Okay. So first of all, this work primarily focuses on what we call as the edge. Although the term edge is a bit of a fuzzy term per se, because the definition of edge may vary based on the context that we are looking at. It may as well be the edge end user devices, which are also termed as edge, while they can as well be even the user's router, ISP, or even the local edge server. So the variation in the usage of the term edge persists. But however, for the scope of this talk, what we are referring to edge as taking the fundamental tenet of this edge computing networking philosophy, where we focus on bringing the computation as close to the source of data as possible, but it is not necessarily the source of the data itself. So if we take the 5G initiatives, the RANs, RNCs would be the right place to say that we would consider those as the edge clouds. So by definition of edge cloud, what we also mean to say is a decentralized mode of computation that can enable low latency, but has sufficient bandwidth and computational power, not although as much as what a cloud would provide as an infinite scale. Okay, but one thing also to note here is that these edge cloud resources are often limited or constrained in their availability, but they still ensure that you are going to have a low latency services. And several of the use cases like vehicular safety, surveillance, or smart sensing, AR/VR applications demand some sort of these low latency services, which can be promisingly performed at the edge. So if we consider the edge and look at the use cases that are prevalent in terms of like image recognition, AR/VR, NLP, or autonomous driving, most often these rely on some sort of an inference service. So by inference service, what we mean is you have a lot of streaming requests, and these requests are run through a set of trained models, DNN, RNN, a variety of models. But most often, like if we talk about image inferencing, audio, video, or text, they typically rely on what we call the deep neural networks or the DNN models, where you run the request through the trained model and try to predict or infer the outcome and send back the response. And all of these, in a way, require low latency services. So the edge rightly fits here to ensure that you can provide the timely inference services. But these DNNs are often compute and data intensive in terms of like they involve several operations like matrix convolutions, activations, etc. And often like they are compute heavy. And in order to meet the timely requirement and process them in real time and achieve low latency, you typically need some kind of an accelerators that can allow you to meet the latency constraints. But the diversity of the use cases still need to be met at the edge. So what that means?
Question.
Yes.
Or can I ask a question? So do you use GPUs for inference also or just for training?
We use GPUs for inference as well.
Won't CPUs be cost efficient for inference and GPUs for training?
Yes, that is true in terms of cost efficiency, but in terms of latency, I'll just come to that in the next slide to show why GPUs would be preferable over CPUs when it comes to low latency services.
Even for inferences?
Right.
For inference engine?
For inference services. So I'll just visit that point in next slide.
Okay, thanks.
So yeah, the point here is that even at the edge, we need to support multiple applications and rely on DNN for inference services, which need to ensure that you are going to provide inference in real time and low latency. Okay. So overall, if we have to think of the ML inference platform that needs to reside at an edge, on a high note, these will be a typical kind of requirements that need to be met, where you want to utilize, as the edge are going to be resource constrained, you want to ensure that you utilize them judiciously. And for variety of services like autonomous driving, etc., that require predictable performance with low latency guarantees, you are required to process the streaming user data and ensure that you can do inference in very low latency and acceptable latency, whatever the SLO be configured. And given that these are going to be at the edge, and we know that in network, the traffic, the load variations are going to occur every time, then you also need to ensure that the system is able to adapt for the variations in the traffic load, right? And beyond, like if we want to have the edge support variety of use cases, it's implicit that we also need to have the services that are scalable. And moreover, like when we look at these DNN or ML models that are in use, there are several different frameworks that are used, like PyTorch, TensorFlow, CNTK, whatever. So there is a variety of ML frameworks and variety of ML models that run. So supporting such a heterogeneity, even though you have limited resources at an edge, becomes crucial if you want to scale and support diverse use cases. So given these as the outline of the key requirements that we want to go over, now the question came earlier, right? So we want to look whether we want to have CPUs for DNN inference. So we try to say, okay, you can use CPUs compared to the cost benefits they offer. But if you look at the GPUs, nowadays even the GPUs are becoming more and more affordable than what they used to be. And considering that you are trying to build an edge cloud, it's even possible that you can have some of the GPU instances applicable. So to put it in context and see what is the benefit of having the GPUs for inference purposes, we conducted this experiment. And note that this experiment was conducted on a server grade machine. And the CPU here refers to what we have called the Dell PowerEdge nodes, which is an Intel Xeon Gold with a 40-core system running at a 2.4 gigahertz with 256 GB of system memory. And the same node, we attached a GPU, that's NVIDIA V100, which has 80 streaming multiprocessors and 16 GB of the GPU memory available. And we use some of the popular inference models like DenseNet, ResNet 50, and VGG. And no streaming, just a base image that is residing. And we want to infer this image using those platforms and see what's the latency we get if we have to infer these images on CPU or on GPU. And you can see here that, note, the scale here is on log scale, right? So if I'm inferring using a CPU, you end up, for one inference, you are ending up in the orders of few hundreds of milliseconds, be it the DenseNet, ResNet 50, or VGG 60. And if we are talking about the surveillance as a use case or autonomous driving as a use case, you typically have to serve a stream of frames that are going to be around 30 frames per second.
I have a question on this. So GPU, how much efficiency do you get? Like how much percentage of compute do you actually use while doing inference?
Yeah, very good question. Yeah, so this is a very right question. And the rest of my talk is based on whether the GPUs are really going to be utilized rightly, because they provide massive parallelism and massive support, but they are often underutilized. And we'll get into the context of in the next set of talk about where the lag happens, where is the lag in proper utilization of the GPUs, and why we need something beyond to utilize the GPUs better.
And you used NVIDIA kernels, is that correct?
Correct.
For V100?
Correct.
Okay.
Yeah. So just to get back to here and to put the things in context. So like here, like we said, like we considered these three popular models, and you can see that when we use the GPUs, you are able to have a very low, like the order of magnitude difference in the time that you need to infer, as opposed to the GPU, which is a server grade machine of the best high-end quality, right? So even the NVIDIA V100 GPU with single inference that's already existing, you can see that or across all these three models that we are presenting here, you are able to get it in less than a few milliseconds of time. That means if I were to utilize these machines, I would be definitely ensuring low latency inference service, right? So that puts the context for us to say that if we want low latency or real-time inference service, although expensive, GPUs would be more appropriate. And the rest of the talk is towards trying to see, okay, if GPUs are appropriate, what are the concerns attached with them and how we can make them better. Okay, so if we look at this result earlier and see why GPUs are really helping, and we can see that like this is the NVIDIA source from the V100 GPU. And you can see that GPUs offer a lot of streaming multiprocessors and each processor supporting several of the cores. And you can see that SMs around 80 and there are around the tensor cores around 40 of those in a V100 GPU. And each of these streaming multiprocessors again have several of cores, like 32 cores per streaming multiprocessor. And overall, they are able to provide several teraflops of computation power. And this massive computation really enables us to achieve a very low latency inference service as opposed to using the GPUs. But the question again, like was asked earlier, it becomes evident to see like, okay, we have these GPUs that are providing massive parallelism and have a lot of latency hiding techniques, but when we are trying to do inference, are they effectively utilized? I mean, what's the effective utilization of the GPUs in terms of if they are providing these many teraflops, how much of the computation power am I really using? And this prods us to see like what are the current challenges here in terms of GPU utilization and how things go on, like to see what can be done to improve it further. Okay. So first we try to analyze if we put the GPU utilization on context and try to analyze how these different DNN models behave in terms of utility. So there is two ways that you can do. One, a black box mode where you try to send the requests and see what's the behavior in terms of latency and throughput. And the other is to get into and find the parameters that they're reported by the GPU to see like a white box approach, which says what's the exact utilization of the GPU. So if you look at the NVIDIA GPUs, they give what we call as a GPU occupancy. And unfortunately, that number, if you are trying to, even if just one of the streaming multiprocessor and one of the core is active, it reports as 100%. So even if the rest of the 32 SMs are idle, while only one of the core in one of the SM is working, reporting utilization of the GPU as 100% is definitely wrong. And you cannot take that as a number to say what's the utilization. So we tried to devise our own metric. That's actually, I didn't include that in the part of this paper, but from the black box mode of how you can try to really utilize, identify the GPU utilization, one approach is we can feed the requests at whatever the best rate that you can, see what is the throughput that you achieve and what is the latency that you can give. And that's what we try to analyze here as a black box mode. And what we try to do further is with NVIDIA V100, you have the ability to contain the number of GPU resources that you want to allocate for running a particular application. So we start with a means where we set a variation. We keep on changing the number of resources that we want to allocate for a given application and see the impact on the inference and throughput. Okay, so we considered the three different models here. Like we said, ResNet, VGG 19 and 16 are the image-based inference DNN models. And Jasper is a audio based, like the model, while GNMT is the Google's translation, the text NLP-based model. So we try to use these three different categories to see how would they behave for audio, video, and image inferencing services. So here you can observe that we start with a very small GPU percentage. Like when we say GPU percentage, what it means is if I say 5%, it is the number of SMs that are going to be allocated is 5% of the 80 SMs that are available. So that means 4 of the SMs will be allocated when we set the GPU percentage as 5 for that application. And we keep on increasing the applications level. Like we start with 100 and in fact we go other way. It's either way, like the experiments can be conducted. But once we start to analyze what we can see, like as you keep on reducing the GPU percentage or reduce the number of resources to a larger extent in this area here that we are speaking about, like if you look about 40 to 100% in most of these GNMT or Jasper or even these ResNet, VGG and VGG19, there is almost no improvement in latency as you go from 100 to the low, as you go from like 50 to 100 in increasing steps, you don't see any improvement in latency. While you go further below to the left, like beyond below 30, then you start seeing there is a sharp increase in the latency. What that means is the real utilization of these models in actually using the GPU resources is very limited, meaning your actual utilization of the resources for different DNN models for a given GPU seems to be very, very low. And the same when we look at the latency and the throughput, you can see the same, like the improvement in throughput as we increase the GPU percentage, it more or less saturates at some level for around 30 or 40. And then there is negligible improvement in the performance of the throughput that you get by increasing the GPU percentage, right? So what we can see here is that these resources are definitely not completely utilized when we look at the entire GPU resources that are going to be used for an inference service. So that's the takeaway from this message here, that most DNN models that we use, although there are several DNN models where the utilization can be seen like it increases and the inference throughput and latency, you gain significant improvement as we increase the resources. But most of the DNN models that we see today need not fully utilize the GPU resources. So that's one of the main things that we need to understand and see how we can really improvise on it further. So there have been already, like this has been not the first to showcase that. There have been other works that have also tried to show the same aspect. And one of the accepted approaches, if you want to increase the GPU utilization, has been that you want to batch. Instead of doing one inference at a time, you would want to batch a bunch of inferences or batch a bunch of requests and infer them at a time so that you mitigate the overheads that you have in terms of CPU-GPU interaction and ensure that a kernel can execute efficiently and utilize large number of threads that the GPUs provide. But we also see, like if we are trying to speak about the inference at the edge, unlike the machine learning where you can go with a very, very large batch size of order of thousands, here when you are trying to infer, you're limited by whatever the SLO constraints and whatever the real-time latency constraints that you have to meet. That means the batch sizes are typically shorter, like you can go from maybe up to hundreds. So here we consider the case where to say that if we had earlier shown with a batch of 1, now if we keep on increasing the batch size to batch size of 2, 4, 8, 16, and so on, what is the impact that we see in terms of latency and performance? Again, as similar to earlier experiment to see how does these two things behave when we are trying to change the GPU percentage while running these models at different batch sizes. So for this result here, we show only the AlexNet model, but we also profiled the same for other models, and our findings were similar. And in fact, the other models like Jasper and GNMT, there were much less of GPU utilization, even if we increased the batch size. But here, as a best case, what we can see here is even if we use the AlexNet model and increase the batch size, we see that for every case, there is a point where we start seeing this diminishing return. Like what we call as a diminishing return is the decrease in the latency as we go forward with increasing the number of allocated resources for performing the inference for various batch sizes. You see that the improvement that you can get keeps reducing as we keep on increasing the GPU percentage or the resources that you want to allocate for executing a batch. So what this point here we call like one of the observations that we make, and then we say that for regardless of the batch size, what we see is there is a certain point beyond which the performance or latency improvement reaches a point of diminishing return. And we want to basically ensure that you are able to operate at a point where you have the right usage of the GPU resources and ensure that you are able to meet the latency. So what that means is, if I have a latency requirement of 30 milliseconds, I'm fine to operate with just 10% of GPU for a batch of 16 because I'm still able to meet that requirement. While if I have a latency requirement of 10 or 15 milliseconds, then the same point doesn't serve my purpose, right? So this is where a trade-off between how you can try to utilize minimum of the GPU resources that can allow you to operate within the required latency constraints come into picture. So what to realize that, what we say, like all the models, we can have a knee point, which seems to be a point where we can say that beyond that, you are not going to get any additional benefit. So better not to operate the models having higher number of resources on the GPU. And if you want to operate on a low other side, then you want to trade off between what is the latency that you want to achieve and what is the correct GPU resources or GPU percentage that would allow you to operate with a given batch size in that and ensure that you are able to meet the latency. So these are the characteristics that we want to take ahead. And then like the takeaway point here is that we want to be allocating the GPU resources within the knee point and trade off between the latency and the batch size that you want to operate with. Okay, so and allocating a GPU resource beyond a certain knee point is always going to result in a wastage of the GPU resource because you are not efficiently utilizing it and it's not helping in any sense either, in either reducing the latency or improving the throughput. Okay, so to summarize the whole picture in terms of what we are getting towards, the main thing is we want to build a timely inference service at an edge, and we want to utilize the GPUs. So the problem statement now is, if we want to utilize the GPUs, what are the constraints that are tied to it? And what are the challenges that we need to overcome? So typically when we look at the GPUs that you want to use for inference, the major challenge is typically only one application at any point can access the GPU. So what that means is that you can have the entire of the GPU, but only one application running on it at a time. And this has been the traditional model of using the GPUs. And you can, however, have multiple applications that run, but they are going to eventually time share the GPU, and the GPU is going to be time shared across multiple applications. And automatically this time sharing results in a lot of other consequences like latency degradation, limited scalability, and in fact, like what we showed earlier, like if only one application's kernel is running at any point, it is definitely not utilizing all the GPU resources, resulting in massive wastage of the GPU resources. So these have been typical challenges. And our goal now is, if we want to address this problem, then we want to ensure that you want to build a system that can overcome these challenges. And when we say that they want to overcome these challenges, you want to ensure that you are trying to build a system that can provide predictable latency for diverse ML inference applications, a multiple number of them, which also means that you want to ensure that you want to be able to support a large number of inference applications that can run on the GPU at the same time. And at the same time, you want to, together, if you culminate it, you want to efficiently utilize the GPU resources so that you can scale to large number of applications and ensure that you have predictable latency. So both are tied. So in a nutshell, what this whole of the solution would be to like what the way we have been doing the virtualized instances of machine to utilize the server machines in a better way, we can as well have the virtualization of the GPU resources so that different virtual instances can run parallelly. And what that means too is like in terms like you want to space multiplex the GPU resources and ensure that you can utilize most of the GPU resources across diverse set of ML applications. So this is a nutshell of what the whole work speaks about, but we'll get into the details of like what are the consequences of utilizing a time shared system and coming towards this spatial multiplexing. And there have been several works that have in prior also have tried to use this spatial multiplexing. Okay. So to put things in context, if we are using temporal sharing or the traditional approach of multiplexing the applications, wherein the kernels of different applications are interleaved and executed serially, so the user perceives concurrent applications are running while in reality, they are all sharing the GPU one at a time. So we conducted an experiment with 3 different models. Again, like the ResNet 50 as the inference R1 and R2, and another model VGG. So we time step these inferences. Okay, like to begin with, we start with R1, and after 10 seconds, we launch another instance R2, and after another 10 seconds, we launch V. That's the VGG instance. So you can see here, like this result is the plot of what we see as the inference and throughput and latency that we get when we run this experiment. So what we can see here, like in the first 10 seconds, like there's only a R1 that is running and it gets around throughput of 150 inferences per second, and its latency lies somewhere around 7 milliseconds. And as we go to 10 seconds, another instance of R2 is launched. And when we have the another instance time share, you can see that the latency increases right here. So you can see like as soon as we bring a new instance, latency increases. Why? Because now both the instances are time sharing the same GPU, each run one after the other. And as we bring in another VGG instance right after 20 seconds, you can see that inference latency again degrades for these R1 and R2, as well that you can see that the inference latency for R3, that is the VGG model, shoots well above 60 milliseconds. And if my SLO was somewhere in the range of 50, then I've already violated the SLO, and that means I cannot potentially time share this VGG with R1 and R2 if this is the scenario with time sharing. And as we decommission the instances again, you see that there is a variation in the latency that occurs and likewise in the throughput. And the black thing here captures the overall throughput that you get over a time while trying to time share these instances. So you can see that as the instances come and as the instances leave, there is a variation in the throughput as well. So what this temporal sharing mechanism allows us is you can execute to an extent, provide concurrent execution, but it doesn't meet either of the requirements that we set with. So several works also explored about spatial sharing, and with NVIDIA, we have what we call as the CUDA NPS mode. That's the default mode, which supports parallel execution of kernels from different applications. So now here, instead of time sharing, you are sharing the resources of the GPU and allowing all the applications to execute in true sense in parallel. So now if we conduct the same experiment and in the default spatial sharing mode, we can observe that to begin with, like you had similar throughput with single running model. And as the second model is launched, you can see that the latency, whatever you were observing earlier, there is a variation still, and the variation increases further when the third model comes up. And likewise, the throughput also varies across these things. So what we observe is that parallel execution helps. And you can see that compared to the top, if you compare to the bottom, we are able to contain the latency of all the applications. Although you can see that the latency of R1 and R2 has jumped to what it was comparatively lower, but it's still like if you had SL of 50 milliseconds, you are able to meet the constraint for all the three models. Now, the green is also within acceptable latency, the processing. So that way, you can see that it is able to support multiple models, execution of multiple models within an acceptable range of latency. And also, like now, as the resources are shared across these three models at the same time, you have the improvement in GPU utilization as well. But again, if we look at the variations in the latency that you observe, it is similar to what happened in terms of how the latency variations occurred as the instances were commissioned and decommissioned. So still, you don't meet the predictable performance requirement, right? So then the question becomes like, yes, we have a spatial multiplexing that to an extent helps improve GPU utilization and improve scalability. But then how do we go about to improve or provide a predictable performance with this spatial mode of multiplexing? And that's where like there were recent advancements that were done with CUDA MPS, where they proposed like the whole of the issue that comes when we were trying to multiplex is how you channelize and allocate the resources in the GPU. So if in the default mode where the resources are going to be shared amongst different models, whoever has the hungriest model wins majority of the resources while other instances might suffer. But if I'm able to overcome this problem, then what that means is I should be able to control the number of resources that each of the model can get. So the CUDA MPS facilitated what we call the controlled MPS mode, where user can dictate and set what is the maximum GPU resources that each instance can take. For example, if I show you here a plot, like if I have 84 SMs and I want application 1 to utilize just a portion of them, like 15% or 12 SMs, while application 2 utilize 30% of them and so on. And this support exists, and that's what we refer to as the controlled MPS mode. And now if we reiterate the same experiment in the controlled MPS mode with R1 and R2 each getting 25%, while the VGG gets 50%, we can see that no matter when an instance is commissioned, when an instance is decommissioned, you have a predictable latency. There is no variation in the latency all along. Although you see that the latency now, like the 50%, ensures that you are within the 50 milliseconds bound, but the tuning of the resources has direct impact on what will be the latency. So that's something we need to consider. But in a nutshell, the controlled spatial sharing ensures that you can have predictable latency. So that solves one of the hurdles that we saw earlier, which was not possible with the default MPS. But if we have to take along these, like although on onset it seems that all the problems are solved, but there are a lot of caveats in using the controlled MPS mode as is. So if we look at this model again, like the results that we have on the right is with the controlled MPS, and juxtapose that with the results that we have when we try to use the default MPS mode, where we saw there were latency variations. But if we observe carefully in the instances of the first 20 seconds here and the last 10 seconds here, what we can observe, like one, here we are underutilizing the GPU resources because only one of the application is active and that's only going to utilize 25%, and here up to 50%. And in fact, when you could have served the requests a lot faster and a lot earlier, you are serving only a small portion of them. So your overall throughput is also lower, right? So at either of the edges, what that means is there can be the choice of going with controlled multiplexing can result in underutilization of the resources, which you don't want. And this underutilization also means that you may not be able to scale further because both are interlinked, right? So you need to ensure now that if the resources have to be apportioned, you need a mechanism that can manage these resources properly. And moreover, like the current mode of how you can set these resources, whenever the application comes up, you need to set it up at a priori before loading the application onto the GPU so that it knows what's the portion of GPU that it wants to run. And once you want to run it, and you cannot change it anytime in the lifetime of the application. But if we want these to serve streaming applications where load can vary over time, you definitely want to adapt to the load requirements. That means you should be able to adapt the GPU per resources so that you can meet whatever the traffic requirements. If it is high, you would want higher GPU resources. If it is low, you would want to basically give up the resources and ensure that you can run within the prescribed SLO. So given these, like what we can say that challenges exist in terms of how you can typically ensure that you can use this controlled spatial sharing mode and still ensure scalability and utilization of the GPU resources properly. So to address these exact challenges, we built our system that's called GSlice. And this GSlice basically provides a generic or an integrated inference platform. And by integrated or an inference platform, what we mean is a single platform that can support different ML frameworks like PyTorch, TensorFlow, CNTK, TensorRT, and so on. And we also want to overcome the challenges that we saw with controlled spatial sharing of GPUs. And in order to do that, our platform incorporates these characteristics. Like we build what we call as a dynamic resource provisioning scheme that allows multiple ML or inference applications that can run across multiple GPUs with the rightly tuned GPU resources that they want to be utilizing to meet the application requirements. And we also build a SLAB, what is self-learning and adaptive batching scheme. And this scheme runs for each of the ML inference application to determine what is the right set of batching that you would want to do so that you end on what we saw on the left of the knee point, ensuring that you are able to meet the SLO requirements for each of the applications, no matter how many other applications are run concurrently and multiplexed spatially. And when we want to scale, like there is also another important aspect that we need to remember, like most of these DNN models, they come with huge weights and bias parameters, sometimes in the orders of GPs. And if you have a GPU that has a limited memory, you want to be utilizing the memory of the GPU judiciously. So if I want to run one instance of an inference service and try to run another instance, basically the footprint on the GPU would be double. So we looked at like what are the ways that we can minimize that, and we came up with what we call a parameter sharing scheme that allows to drastically minimize the footprint of different distinct applications that run, which are going to use the same weights and parameters. Besides this, there were several other streaming platform specific optimizations that we did, but for the most part of this talk, we will cover only the higher part of the things. So any questions up till here? Okay, so I take silence as no questions. And so let me first get started with presenting the overall GSlice architecture. Like I said, this is a plan to be run on edge cloud nodes, which are server grade machines that have the DGPUs installed. So on a high level, like I'll explain basically the key components and how we built this platform. And this GSlice is built upon Reinforce, an OpenNetVM-based DPDK platform for providing high resiliency network function virtualization platform. So we use that as a base model and build the components. I'll walk over each of these components one by one to cover the different aspects. So first, to highlight the software stack of our proposed platform. So we run on top of a Linux-based operating system and use the NVIDIA CUDA MPS as a base. And then we integrate that with the DPDK so that allows for basically ensuring a low latency data transfer and processing of the packets from within the CPU, and also transfer the packets to the GPU. So crux of our work, the ones that we have highlighted in blue and the ones that we have highlighted here in yellow, the inference framework and inference functions, because we want to facilitate diverse inference functions that can hook and run on our platform, like PyTorch, TensorFlow, CNTK. So we built these functions, and hooks that are provided to different inference functions. Although what we mean by hooks is we need to modify a very thin layer or a shim layer of the functionalities in different frameworks to enable them to work with our platform. So the core of our work then consists of like how we facilitate transferring of the packets from the machine to the inference functions over to the GPU and ensure that you can run the inference in low latency. So for that, we basically build a shared memory concept, like the huge pages that we use for DPDK to ensure that you can directly pass the packets to the user space where the current applications, inference applications run. You want to also ensure that whatever the inference data that you request that you achieve are going to be shared at a very low cost to the GPU. So we use what we call a pinned shared memory model, and the shared input-output buffers that are required for GPU to process on. And we use what we call the GPU resource allocation manager that basically is agnostic to the different inference functions or the frameworks, but is aware of the system characteristics, what CUDA instances is a cluster or a single instance that you are running, and ensure that you can channelize the resources correctly. And we also use this inference model loader that basically keeps track of what are all the inference models that you want to run with different platforms so that you can reuse, like I said, the parameters for one model across the other. And the external component that we use is an orchestrator. And here the role of an orchestrator is to ensure that you want to monitor the system resources, see how these instances are behaving, whether they are within the SLO, whether you want to bring up a new instance, scale the instances, and these characteristics are handled by the orchestrator. And from the application standpoint, you would want to run the inference functions that are going to like CNTK or PyTorch that are going to load a particular model and execute them. And for them, we build this libml, which provides different functionalities. Like one, given a framework that is running, what is the correct batch size that you want to run? So that's the slab or adaptive batching scheme that we want to run. And given that you want the packets that are received on the node and transferred over to the GPU, what is the best way, that light way that you can do? Like there is a GPU direct that allows you to transfer the data without bypassing the entire CPU. But you want to ensure that you are able to aggregate the batch and ensure that you can transfer. That means you have to transfer the data over to the CPU. But if you can eliminate the copy from whatever the NICT transferred packets over to the application space data and then transfer it over to the GPU without copy, we build this DTTX model that uses the pinned shared memory approach to ensure that you can transfer the packets without involving multiple copies. And we also build a buffer pool and stream engine that ensures that you are going to use the shared input-output buffers with the GPU rather than allocating them on runtime. Okay. So this leaves us with a scheme that you have a platform that is able to run multiple applications, but now the crux of the platform is how would it dynamically provision the resources for each of the ML applications. So like we put the case earlier, like why you need the dynamic provisioning of GPU resources. It's primarily that you have to adapt to the variation in traffic demands. You have to ensure that you have to meet the resources. If you are not able to meet the SLO, you have to basically repurpose and see what can be done to increase the resources to meet the SLO, or like we saw in the use cases where there are addition or removal of IF instances, then you would want to ensure that you are able to, again, reclaim whenever the instances are given up and use that resources appropriately. So given these scenarios, what we built is a resource tuning algorithm So here, like the main, I think I'll not get into the details of what exactly we do, but a high level to tell like what factors that drive this GPU resource tuning algorithm is for every inference, we want to monitor what is the current latency that it is observing in terms of providing the inference and whether it is meeting the SLO requirement. If not, is there a slack? If it is meeting, is there enough headroom? So either of the cases, what that means as a residual latency, would allow you to reconsider the resources that you want to allocate for that particular instance. And likewise, like if there is a throughput required, because the traffic arrival, like the arrival rate, determines the demand in terms of what the inference function has to cater to. And the throughput that you actually get from executing a batch of inference is what you have as a serving rate. So you want to ensure that you balance the serving rate with the arrival rate. So, and also see that if you have any headroom, especially in terms of serving rate, typically you will have like you lag, there will only be a slack. But if you want to see that whether the resources that you have are over allocated or under allocated, so we use these aspects to determine like when a GPU resource would have to be fine-tuned, retuned. And this tuning algorithm runs periodically to check for each of the inference functions that are going to run. And like we said, this libml is a part of each inference function. So this is run within each of the inference function individually. And once we compute, you are able to determine whether there is a need to reallocate the resources and what is the means that you can reallocate. And we used a threshold parameter that's again a tunable, which helps accommodate the variation, because if there is a very minor increase that you want to go for or a minor reduction, you are unnecessarily paying a lot of cost in trying to retune the resources. So this threshold helps accommodate variations and ensure that you avoid the oscillations in the resource allocation, because you allocate some and you see that you are now over provisioned and you want to give up. So you want to avoid these kind of cycles. So having a good threshold would help us understand what would be the right allocations that you can manage the resources. So the overall part is now the resource computation. And once you have the residual latency or residual throughput, we should go ahead and try to see what is the proportional resource requirement based on the current resource and the current observed slack or headroom and reallocate the resources. And now remember, like this is running for each of the inference function. And when we are having multiple inference functions that are running on a single node, then you have to some way allocate the resources across all of them. And sometimes you may be able to meet, sometimes you may not be able to meet. But ensuring that you can allocate the resources fairly, we try to use a max-min fair allocation scheme across all these instances that are opting for variation in the resources, and ensure that you can meet all of the requirements. If you are not able to meet, that means there is an admission policy change that you need to do so that your resources cannot meet the required constraints of meeting either the SLO or the arrival rate. And whenever this kind of an operation needs to take place, like we said, if at the time of application bring up, you have to allocate the GPU resources. Now that means if I have to retune, I have to rebring another instance back up. And to initialize the GPU, set up the framework and bring up the instance, the penalties is very huge. And we have observed that if you're doing for CNTK or PyTorch frameworks, it varies somewhere in the orders of 2 to 15 seconds. And especially that is true with PyTorch, where you are trying to allocate the CPU and GPU resources upfront and keep all the resources reserved. It takes more amount of time to initialize the GPU and load the model. So now the next challenge is how can we overcome this if we have to retune, but at the same time, we don't want to pay the penalty of overcoming this huge gap, penalty of huge downtime. So we leverage what we call the shadow inference functions, where for every instance, we host another instance that is also running at the same time, but it has not initialized anything with GPU. So it is free to go up with whatever the GPU percentage that you want, and it can be done on the runtime. So how that happens is basically what we run as an overlapped execution beyond having this shadow inference. So it's a 3-stage process where you have actual inference function that is configured to run with whatever the GPU percentage. And you have a shadow inference that is basically in sleep mode, which has not yet initialized GPU or operated with any instructions on the GPU or handling any packets. It's just a process with memory instance or a container that's lying idle. And once you want to switch over, once this GPU resource allocation is being determined, you want to ensure that you know the correct GPU percentage that you want to set on the shadow. Then first you specify the exact GPU percentage that you have computed, and still let the actual instance keep running so that it can keep continuing to do the inference with whatever the old value rather than taking it down right up. And then once the inferences continue and this takes its own sweet time to get itself up and configure the GPU percentage, over that period of time, what you have basically done is oversubscribe the GPU in terms of making that the GPU resources are going to be used by both the shadow and the original inference function, but the shadow is not going to do any active GPU calls, so it's still fine. It doesn't impact the performance of the primary function. And once entire setup is being done, you want to then ensure that you can reroute all the traffic towards this new instance and ensure that now you are able to run the instances with the right amount of GPU percent resources that it requires. So that way, the policy of make before you break ensures that you can have the overlapped execution without having any impact on the predictable performance that we want. And at the same time, allows you to have a downtime of the orders of just around 50 to 60 microseconds. And this is the time that you need to basically notify and switch over from the current active to the new active or a shadow IF function. So this switchover mode allows to ensure that you are able to operate with almost zero downtime and ensure that you are able to come up and retune the resources in a much faster way. So that's the whole of how we can retune and ensure that a platform can build and support running the resources, GPU resources judiciously. And now within the inference function, like every time we change the resource, there is a change in how a batch need to be formulated, right? So that means a typical adaptive batching schemes that existed would not work unless we want to learn the current spatial share of a GPU that we are configured with and ensure that we retune the batch size to accommodate the changes that can happen for the current configured GPU. So we compute that again in the same, like we have available headroom that we can keep track of. And this allows us to track whether an instance is being over-provisioned or under-provisioned by computing whether it's a positive or a negative headroom and ensure that you can basically pull up or pull down the resources or increase or decrease the batch size and still operate within a specified SLO. So I think in the interest of time, I'll skip over this parameter sharing. Basically, this shows like when I said we can use the weights and bias parameters that we use for a model to be used across another instance that allows you to lower the load time in the order of seconds to few milliseconds and also reutilize the GPU, enabling you to pack more instances, automatically improving the scalability. So I'll quickly run through like what like one of the evaluation results, but we try to do as an overall holistic platform, how this really helps. So we focus primarily on the image recognition tasks. And we can see that if we use the traditional MPS here, like the experiment here tries to compare if we use the traditional default MPS, which is coming with the CUDA, and you want to augment the slab to that MPS so that you can adaptively batch, and overall GSlice with the entire operations of the other aspects that we discussed in terms of resource tuning, updates, and optimizations. You can see that overall from the throughput perspective, we are able to improve significantly. And this throughput is capped in terms of how the latency behaves. So if you look at how the latency, like we are ensuring that whatever the specified, like if 25 milliseconds is the SLO, then you want to ensure that you are able to operate right at the observed SLO and not exceed that. So in either of the cases, based on whether you are able to meet the latency requirements, as well as ensure that you are able to achieve larger throughput. And likewise, like the state of the art is basically the Triton or the TensorRT server. So we run the same experiments with TensorRT and with GSlice on the same machine. And we can see that GSlice is able to outperform TensorRT in several ways and also ensure that the GSlice is able to meet the latency requirements, while TensorRT in some cases is like you can configure the latency requirements for a TensorRT when you run the TensorRT container, but still you can see that there are some variations that occur which basically violate the latency requirements. But in our case, we can see that you are able to meet the latency requirements in all the cases. And the crux of the part is basically when we want to have scalability and run multiple applications. So here, like the result shows here, if you want to have multiple combination of the applications, our results still show that if you're running GSlice as opposed to running just the default MPS or just the slab, you have tremendous improvement in the overall throughput of the system, as well as ensure that you're able to operate within the latency constraints. So overall, like the results that we have shown showcase that GSlice as a platform is able to achieve scalability, ensure that you are able to have a predictable performance, and guarantee this latency requirements for all the applications. Okay, and whenever we have this adaptive batching, what is important is like we want to converge as quickly as possible so that you are able to meet the SLO requirements as quickly as possible. And there were already the state-of-the-art works like Clipper, which also tried to do the adaptive batching. But when compared with Clipper and the approach that we are proposing of trying to fine-tune the adaptive batch with self-learning approach, we can see that there is a magnitude of difference in terms of how we can quickly converge. So like the GSlice is able to converge in few hundred milliseconds, while the Clipper takes around 3.5 to 4 seconds here to actually converge and identify the right batch size. So overall, this work tries to provide what we have a generic or integrated inference platform, which can support PyTorch, TensorFlow, CNTK, and TensorRT. And it's possible to support other frameworks, but it requires some tweaking of the framework so that they can adapt to the libml functionalities that we provide. And overall, we demonstrate that controlled spatial sharing can be utilized to provide guaranteed performance isolation and at the same time ensure that you can utilize the resources better and achieve large performance improvement. And this dynamic resource provisioning scheme with shadow inference function and overlapped execution allow us to ensure that you can have as low as less than 100 microseconds of a downtime to operate reasonably in a fashion with zero loss. So overall, like these are the aspects that other aspects that allow this platform to be integrated and work as a edge inference platform. Okay, I'll not get into any of these details, but I think we can end here.
Thank you, Dr. Samir, for a wonderful talk. I think